When we think about building the future, we usually imagine adding things together, right? Like we build higher skyscrapers, or we write longer lines of code, or, we stack batteries to get more power. It's this very additive structural process.
Yeah, we build outwards, we accumulate. We just assume that adding more material or more complexity is always the answer.
But what if the ultimate key to our future isn't about building something new at all? What if it's about, like, trapping something ancient?
Oh, that's a great way to frame it.
Right. So, welcome back to the Deep Dive Classroom Divers. I am your host, and today we're unpacking a truly wild lesson. But real quick, before we get started, make sure you hit that like button, subscribe to the channel, and check out the affiliate links below. Oh, and we've got some brand new fourth wall merchandise up, so grab a shirt and definitely suggest what topics you want us to cover next in the comments.
Yeah, those comments really help us shape future lessons.
Exactly. So, divers, today's mission is unpacking one of humanity's absolute holy grails of technology. We're talking about nuclear fusion, specifically how scientists might have just simultaneously solved two of the most stubborn roadblocks standing in the way of limitless clean energy.
It's a genuinely thrilling moment for plasma physics. I mean, we are looking at a paradigm shift in how we handle the extreme, incredibly destructive forces inside these reactors.
And to guide our exploration, we are diving into a May 2026 article from SciTech Daily. It's titled, Taming the Star, Solving Heat and Stability in Fusion Plasma. So, okay, let's unpack this. Fusion requires heating matter to temperatures that are actually hotter than our sun.
Tens of millions of degrees.
Tens of millions. And then you have to trap that superheated matter, which is called plasma, in powerful magnetic fields. It sounds like pure science fiction, but this is actively happening in laboratories right now.
Right, and the sheer scale of the engineering challenge there. It really cannot be overstated. You are taking the hottest substance in the solar system, which is this violently swirling soup of electrically charged gas, and you are trying to hold it inside a man-made physical machine.
Which just sounds impossible.
It creates extreme engineering nightmares. The absolute key to viable commercial fusion energy isn't just making it hot. It is finding a way to balance intense heat control with plasma stability. If you cannot do both at the same time, well, you don't have a power plant. You just have a very brief, very expensive science experiment.
Let's bring you, the listener, inside that machine for a second. Try a quick mental exercise with me. The most common type of fusion reactor is a tokamak, right? It basically looks like a massive, hollow metal donut.
A very complex donut.
Right, a complex donut. And inside that donut, massive electromagnets create an invisible cage to hold the plasma. But the SciTech Daily article lays out what we can call the dual demons of fusion. These are the two violent problems that happen when you try to force a star into that donut.
Let's start with the first demon, which revolves around the concept of H mode, or high confinement mode. In modern fusion research, H mode is essentially non-negotiable.
You have to have it.
You absolutely have to. When a reactor enters H mode, the plasma forms this very steep, pronounced pressure gradient right at its outer edge. It essentially creates its own insulating barrier. This is fantastic for keeping the core unimaginably hot and trapping the energy efficiently.
So it's like a thermos ceiling in the heat. But earlier when we were reviewing the notes, we realized the flaw in that thermos analogy, right? It isn't a solid object. It's a churning storm of electromagnetism.
That is the perfect way to visualize it. And because it is a churning storm, that steep edge, that beautiful insulating barrier, is highly unstable. The pressure builds up at the edge of the plasma until the magnetic field lines literally warp and snap. And this triggers the first demon, which we call edge-localized modes, or ELMs.
ELMs. And the article compares these ELMs to solar flares, right?
Exactly like solar flares.
So these are sudden, violent eruptions of heat and high-energy particles bursting out from the edge of the plasma, and they slam directly into the reactor walls.
They act like rapid-fire, microscopic explosions that severely damage the interior wall of the tokamak. For an exercise, I want you to imagine holding a highly pressurized balloon that randomly shoots jets of fire out of its side.
Oh, wow, okay.
Yeah, that is an ELM.
Which raises an obvious question, right? If H mode is so volatile and it constantly generates these damaging solar flares that wreck your billion-dollar machine, why on earth do scientists use it? I mean, why not just run the reactor in a mode that doesn't constantly explode?
Well, it is a frustrating catch-22 for physicists. Scientists use H mode because
Mm.
right now it is our only reliable way to efficiently trap enough energy to make fusion worthwhile.
So without it, it's useless.
Right. Without that high confinement edge barrier, the heat leaks out of the core way too fast and the fusion reaction simply fizzles out. You do not get enough energy out to justify the massive amount of energy you put in. So you need H mode for efficiency, but H mode brings these destructive ELMs that tear your machine apart.
Let's try another mental image for the divers listening. Imagine you are trying to contain a raging tornado, and the only tool you have is a ring of massive industrial fans blowing inward.
Oh, I like this.
Right. So you need the tornado to stay intense to harness its power, but the wind is so erratic that violent gusts keep lashing out and ripping the blades off your fans. But you can't turn the fans down or you lose the tornado. You're just completely stuck.
That captures the volatility perfectly.
Mhm.
And that is really only half of the nightmare. Because while the sides of the reactor are getting pelted by ELM solar flares, the bottom of the reactor is dealing with the second demon, which is the divertor problem.
Right. So if H mode is non-negotiable and the sides are sparking with solar flares, what exactly is happening at the bottom? The divertor, as the source explains, is essentially the reactor's exhaust system.
Yes, the exhaust.
Even with the best magnetic fields in the world, some of that superheated plasma is just going to escape the main core. So the magnetic fields are intentionally designed to funnel that escaping heat and all those stray particles down to a specific region at the bottom of the reactor chamber.
And the divertor plates down there are where the plasma intentionally comes into contact with solid matter. And the heat loads we are talking about are just staggering. The article uses a really brilliant comparison. The exhaust pipe of this reactor has to endure heat fluxes comparable to a spacecraft during atmospheric reentry.
That is insane.
It is. We are talking about intense, searing, unrelenting heat constantly bombarding these metal plates.
Which brings up a really crucial piece of the puzzle, actually, the material of the walls. The source highlights that the breakthrough we're going to discuss happened in a metal wall reactor. Why is that distinction so important? I mean, weren't they always metal?
Historically, no. Many older experimental reactors used carbon for their interior walls.
Oh, carbon, really?
Yeah, carbon is great because it doesn't melt under extreme heat. It sublimates, which means it turns directly into a gas. That makes it very forgiving if you accidentally hit it with too much plasma. But carbon has a fatal flaw for commercial power plants. It acts like a sponge for tritium.
And tritium is the radioactive isotope of hydrogen used as fusion fuel, right?
Exactly.
Ah, so a carbon wall basically absorbs your fuel, locking away the very thing you need to power the reaction and creating a radioactive waste problem right inside the chamber.
Which is a huge problem. So future commercial power plants have to use metal walls, specifically tungsten. Tungsten has the highest melting point of any metal, and it doesn't trap tritium. But tungsten will melt and warp if you hit it with that spacecraft re-entry level of heat for too long.
So if you don't control the heat perfectly, the plasma will literally erode and melt the physical components of the reactor.
Exactly.
So the engineers are trapped between a melting exhaust pipe at the bottom and violent solar flares shooting out from the sides. How have scientists traditionally tried to put out that fire at the bottom without turning off the oven at the top?
Well, for years, the go-to strategy to save the divertor has been a process called detachment. Detachment involves intentionally injecting small amounts of light impurity gases, typically nitrogen or neon, directly into the exhaust region at the bottom of the reactor.
Wait, so they just pump gas into it?
Yes. The goal is for this cold gas to collide with the superheated plasma right before it hits the tungsten plates.
Okay, so it's like throwing a cloud of thick gust into a laser beam. The neon or nitrogen atoms absorb the kinetic energy from the hot plasma. Their electrons get excited, and then they radiate that energy away in all directions as light and ultraviolet radiation. It basically takes that focused laser-like heat and diffuses it outward.
Precisely. It creates a gaseous cushion that partially separates or detaches the superheated plasma from the physical metal surface. It drops the temperature of the plasma right at the boundary layer, which prevents the tungsten from melting.
But, thermodynamics 101 suggests you can't just inject cold gas into a delicate, ultra-hot system without consequences. The source points out a massive catch here. The cooling effect doesn't stay put, does it?
No, it doesn't. And that is the historical roadblock. Neutral gases don't care about the magnetic fields holding the plasma. When you inject neon to cool the bottom of the reactor, that gas tends to creep upwards, migrating back toward the main plasma core.
Ah, and when it creeps up, it hits that beautiful, delicate H-mode barrier we talked about earlier.
Yes. It overcools the plasma edge. The steep pressure gradient degrades, the insulating thermos effect breaks down, and the plasma just drops out of age mode. It is a razor-thin Goldilocks scenario. Inject too little gas and you melt your tungsten exhaust,
Right.
but inject a fraction too much and the cold gas creeps up, smothers the edge, and kills the fusion reaction entirely.
So for decades, solving this paradox like eliminating those violent ELM solar flares, protecting the divertor exhaust, and maintaining that high confinement energy without smothering it, that's been the ultimate puzzle. You fix one thing, you ruin the other.
Which brings us to the core of the SciTech Daily article. Because a team of scientists has seemingly cracked the code.
Okay, divers, here's where it gets really interesting. Take notes on this part. The team behind this breakthrough is led by Professor Gusheng Zhu at the Institute of Plasma Physics, which is part of the Chinese Academy of Sciences. They recently ran an experiment on the EAST fusion device, the Experimental Advanced Superconducting Tokamak. And crucially, EAST is a state-of-the-art machine with a tungsten metal wall.
Right. Improving a concept in a metal wall tokamak like EAST is what makes this a monumental leap. They aren't relying on the forgiving nature of carbon, They are proving this can work in the harsh conditions required for a real power plant.
So Professor Zhu's team managed to create a brand new operating regime. They call it the DTP regime. That stands for detached divertor and turbulence-dominated pedestal.
And the physics behind DTP are incredibly elegant. The team achieved this by using highly precise, real-time control algorithms to inject those impurity gases. They monitor the plasma conditions microsecond by microsecond, feeding in the neon gas with such perfect timing and volume that they achieved what they call partial detachment.
Partial detachment. So they created the cushion, significantly dropping the intense heat hitting the divertor plates, but without flooding the chamber and overcooling the whole machine.
Exactly. That solves the melting exhaust problem.
Okay.
But the miraculous part of this experiment is what happened next. By achieving this precise partial detachment in this specific reactor design, they completely eliminated the violent ELMs.
The solar flares just stopped.
The solar flares stopped. And to top it off, the electron temperature at the plasma edge, the pedestal actually rose, which improved the overall energy confinement.
Wait, hold on. How does injecting cold gas to cool the bottom of the machine end up making the edge of the core hotter? That seems completely counterintuitive. You are adding cold material, but getting a hotter result at the boundary.
Yeah, it sounds strange. To understand that, we have to look at the physical geometry of the EAST reactor. EAST utilizes what is known as a closed divertor design. This is different from older open divertor designs, which are essentially just flat target plates at the bottom of the donut.
Just a flat surface.
Right. In an open design, when the plasma hits the plate and neutralizes into gas, that gas can easily bounce off and float right back up into the main chamber.
Which causes that deadly cooling creep we discussed. So how does a closed divertor actually change that?
Well, a closed divertor is physically shaped with these elaborate metal baffles. It looks almost like a narrow V-shaped hallway or a zigzag channel. When the injected gas cools the escaping plasma at the bottom and neutralizes it, those neutral particles get geographically trapped in those baffles.
Oh, I see.
The physical architecture of the exhaust system prevents the cold gas from easily migrating back up to the main plasma core.
Ah, so the cooling effect is locked in the basement, basically. It can't creep upstairs to ruin the insulation.
Exactly.
Oh.
Because the cooling effect was physically trapped at the bottom, the plasma edge, the pedestal, was shielded. It stopped cooling down. And because the core is still being pumped with massive amounts of heat and the edge is no longer being smothered by stray gas, a very steep, very pronounced temperature gradient forms.
The line between the ultra-hot core and the cooler outer boundary just became incredibly sharp.
Right, extremely sharp.
But wait, if we trace our steps back, a steep gradient is exactly what causes those explosive ELM solar flares, isn't it? The pressure builds on that sharp edge until the magnetic field lines snap. Why didn't this incredibly steep temperature gradient just blow the reactor apart?
This is where we hit the most deeply fascinating part of the physics. The steep gradient didn't snap because of a specific phenomenon it triggered within the plasma. Microturbulence.
Microturbulence.
Or, to use the technical term from the paper, it triggered temperature gradient-driven trapped-electron modes.
Okay, let's unpack temperature gradient-driven trapped electron modes, because that is a heavy piece of jargon. What exactly is a trapped electron in this context, and why is it causing turbulence?
Okay, so inside a tokamak, the magnetic field isn't uniform. It's stronger in some places and weaker in others, depending on where you are inside the donut shape. Because of this, some electrons in the plasma don't just flow freely in a circle. They get caught bouncing back and forth between regions of strong magnetic fields.
Almost like they're trapped between two magnetic mirrors.
Exactly like that.
So you have these electrons bouncing back and forth in a confined space on the edge of the plasma.
Now, introduce that incredibly steep temperature gradient we just talked about. You have a stark energy difference. Extremely hot on one side of the gradient, noticeably cooler on the other. These trapped bouncing electrons are basically riding that steep slope. The stark temperature difference causes their orbits to drift slightly, creating tiny, localized fluctuations in the electric field.
And those fluctuations grow over time.
They do. They grow into microscopic waves or ripples across the population of electrons, and that is the microturbulence.
But, turbulence in almost any other engineering context is an absolute disaster. If you are designing an airplane wing or a pipeline or even a bridge, turbulence causes vibration, inefficiency, structural failure. Why is a turbulent fusion reactor a good thing?
Well, what's fascinating here is that this specific natural microturbulence acts as a microscopic pressure relief valve.
A pressure relief valve. Okay.
Think of a pressure cooker on your stove. If you seal it completely and just let the pressure build, eventually the structural integrity of the metal will fail and it will explode.
Which is an ELM.
Right, that is an ELM.
Oh.
The pressure builds at the edge of the plasma until the magnetic structure violently ruptures. But if your pressure cooker has a little valve on top that constantly whistles, letting a tiny regulated stream of steam escape, the pressure never reaches the breaking point.
Oh, wow.
The temperature gradient-driven turbulence is that whistling valve. Instead of the whole magnetic structure snapping in a massive ELM, these tiny continuous electron waves gently carry particles and heat down the slope, bleeding off the excess pressure.
That is brilliant. So instead of the pressure building up until it explodes in a massive damaging solar flare, this microscopic chaos is constantly gently moving the heat outward. They are using a continuous controlled microscopic leakage to prevent a massive destructive explosion. The turbulence smooths out the pressure gradient just enough to keep it from snapping, while the gradient remains steep enough to maintain that fantastic H-mode energy confinement.
It is a perfect, self-sustaining loop of physics. The closed divertor traps the cold gas, which creates the steep gradient, which triggers the trapped electron turbulence, which bleeds the pressure, which prevents the ELM. They solve the melting problem and the exploding problem through one interconnected mechanism.
So what does this actually mean in terms of tangible results? I mean, we have the physical mechanism clear, but how long did Professor Su's team actually manage to sustain this delicate balancing act?
The team on the East device sustained this stable, high-performance DTP regime for roughly 1 minute.
Now, to someone outside the physics community, 1 minute might sound like, I don't know, the time it takes to boil water. It doesn't sound like a historic epoch.
I can assure you, in the realm of high-confinement fusion plasmas, maintaining this level of stability for 60 seconds is monumental. Remember the hostility of the environment. You have a miniature star swirling inside a metal donut, constantly trying to tear itself apart. Before breakthroughs like this, these volatile high-performance plasmas might only be stable for fractions of a second before an ELM erupted, or the heat flux just overwhelmed the exhaust.
So 60 seconds is a massive proof of concept.
Massive. Sustaining this for a full minute without destroying the reactor and doing it in a tungsten metal wall environment proves that the physics scale to real-world conditions. The ultimate goal is continuous long-pulse power plants that run for days, weeks, or months at a time, providing limitless clean energy to the grid. This 1 minute proves the path exists.
And it is vital to remember this isn't just a theoretical computer model or a simulation. This is a proven physical experiment. The findings were peer-reviewed and recently published in the prestigious journal Physical Review Letters. This is hard, verifiable science that the global physics community is now analyzing.
It provides a very clear roadmap for the rest of the international fusion community. Devices like ITER, the massive multi-billion-dollar international fusion project currently being built in France, will almost certainly look at this DTP regime. ITER also uses a tungsten divertor and requires high confinement operation. This breakthrough from the Chinese Academy of Sciences offers a viable, proven operating scenario for the next generation of mega reactors.
It really highlights the collaborative, iterative nature of global science. So divers, let's look at the key takeaways from our lesson today. Let's marvel at the incredible balancing act achieved here. We started with a seemingly impossible engineering paradox. How do you keep the exhaust system of a fusion reactor from melting into slag while simultaneously preventing the edge of the plasma from erupting in violent solar flares that destroy your containment
It's a
walls?
paradox where solving one problem historically just exacerbated the other.
Right. But by meticulously controlling the injection of cooling gas and using the physical baffled design of a closed divertor to trap that gas at the bottom of the machine, scientists shielded the core. That created a stark temperature boundary, and that boundary caused trapped electrons to vibrate, triggering microscopic turbulence, a continuous tiny shaking that acted as a pressure valve, safely bleeding off heat and keeping everything perfectly in check. Why does this matter? Because it proves stable, limitless energy is within our reach.
And if we connect this to the bigger picture, there is a profound philosophical shift happening in how we understand plasma dynamics. For decades, scientists viewed turbulence in fusion as the ultimate enemy. It was a destabilizing, chaotic force that ruined confinement, a flaw in the system that had to be defeated by brute force and better magnetic engineering.
But this breakthrough proves that we might have been looking at it the wrong way.
Exactly. Nature's complex dynamics, even the messy, unpredictable, turbulent ones, aren't always enemies. When deeply understood at a microscopic level, they can actually be harnessed as tools for stability. We're learning to work with the plasma's natural tendencies rather than fighting them.
I love that concept, harnessing chaos to create peace. It leaves us with a fascinating final thought to chew on before we wrap up. We just saw how harnessing microscopic turbulence can tame star-like conditions here on Earth, essentially using a tiny amount of instability to prevent a catastrophic instability. So, divers, think about this. What other chaotic, seemingly negative forces in nature might actually hold the key to stabilizing our most advanced and vital technologies? If turbulence can be a tool rather than a flaw, what else in the natural world are we fundamentally misunderstanding?
It is a question that challenges the very foundation of how we approach engineering.
It definitely is. Thank you for thinking along with us today. Make sure you practice what we talked about. Try explaining the pressure cooker analogy to a friend today to really cement it in your memory. Keep questioning, keep exploring the incredible mechanics of our world, and remember, sometimes the key to holding a star isn't building a stronger box, but learning how to let it whistle. We will see you on the next deep dive.